Okay, so today we start a very important nuclear reaction, that is nuclear fission, and all our nuclear power plants run on this nuclear fission, which give us so much of energy which we use. Fission is essentially breaking apart a heavy nucleus in two roughly equal parts. So, if you have a nucleus, some nucleus say x, and then if it breaks in roughly two equal parts y and z, and this is these are all so called heavy nuclei and middleweight nuclei. So, essentially a heavy nucleus breaks into two middleweight nuclei. This process is known as fission, or this reaction, nuclear reaction, is known as fission reaction. Now, historically neutron was discovered, Chadwick 1932, and then lots of nuclear physics experiments started bombarding neutron on different materials with the idea that that new elements of higher A value will be produced. So, neutron going into the material, increasing the mass number by 1, and then later on beta decay can convert a neutron into proton. So, that in periodic table you get one higher element. So, this way perhaps transuranic elements can be obtained. So, that was the motivation. So, lots of experiments on neutron irradiations were going on, and that is when 1939 that Hahn and Strassmann were doing this experiment, irradiating uranium, natural uranium sample with neutron, and when they did that, so the product that was obtained, that they were chemists in fact, and so chemical analysis was very strong. So, when that irradiate product was analyzed, they found that there is barium in this. Barium is something like 56 here and around 138, or there are several 6 isotopes of barium which are stable. So, 138 is the most abundant one. So, starting with uranium, which has natural uranium has, as you know, uranium 235, 92 and uranium 238, 92. So, from here one is getting barium. So, originally when they detected this element, they thought this is a new transuranic element having properties similar to barium, but then later on they could detect that it is not something which is similar to barium, it is barium itself. And then they found lot many other elements in this irradiated uranium. So, that means from this 238 or 235 you are getting these medium weight nuclei of something like 130, 140 type of things. So, that was the starting of nuclear fission experiments, and immediately the explanation came in terms of this nucleus as a drop, and then that drop when some energy is given to it, and the drop splits in two parts. So, those explanations came in that same year 1939, and later on Bohr-Wheeler developed a theory in terms of deformations. We will discuss all that things. Now, if I understand it from this binding energy diagram, you remember binding energy of nuclei. If I plot binding energy per nucleon, that is binding energy divided by mass number, and mass number on this side, we had done it earlier in the initial set of lectures. So, with some irregularities here, not very smooth, but then it rises and then it goes through a maximum and then slowly decreases like this. So, this is how the binding energy per nucleon curve goes. This will be somewhere around, let us say 200, 240 like that. This maximum, this the most stable region, this is somewhere around 50 to 60, 56 iron. So, iron, cobalt, zinc, these are the most stable part, highest binding energy here, and then the lighter elements, again you have smaller binding energy per nucleon. So, in fission, the initial nucleus, this X nucleus is somewhere sitting here. So, this heavy nucleus is somewhere sitting here, and then it splits in two parts, and when it splits, the mass number will become roughly half. So, it will come somewhere here. So, from this portions, you are getting 2 nuclei in this portion. If you look at numbers, this here, this number binding energy per nucleon, this number is around, let us say something like 7.6 MeVs per nucleon, and here if you look at half of it, somewhere here, this will be around say 8.5, and of course, the maximum is here, which will be around 8.9 or so. This is all in mega electron volts. So, first look at the rest masses and the energies. If you have a heavy nucleus in this range, and if you look for a reaction of this type, where this X goes into Y and Z, 2 nuclei of roughly equal masses, then what is the Q value? Q value positive or Q value negative? Rest mass decreases in this reaction or rest mass increases in this reaction. So, very simple to calculate. If I take the first nucleus here of mass number say A, and this is mass number A1 and this is mass number A2, from this diagram you can write the binding energy, and remember mass of a nucleus is Z times MP plus N times Mn C square minus the binding energy. So, the binding energy increases, mass decreases, right. So, the Q value is mass of this X nucleus, and minus mass of this Y nucleus and minus mass of this Z nucleus times C square. So, this is Q value is how much, if you have a reaction, how much rest mass decreases in that reaction. So, that is the Q value, that is the energy made available. So, rest mass has gone down. So, that much energy has been made available. So, that is Q value, initial mass minus final mass times C square. So, this you can write your mx is Z1 times mass of proton plus N1 times mass of neutrons, and then C square and minus binding energy, and binding energy of this X nucleus capital A here, and this is binding energy per nucleon. So, this will be, if I take this value here 7.6. So, it is 7.6 and multiply MeV and multiplied by A, right. This binding energy per nucleon is 7.6 MeV, and there are capital A nucleons. So, the binding energy is this much, and this proton mass separately plus neutrons mass separately minus the binding energy, that is this mx. Then my similarly you can write, my is equal to Z2, or let me write this as 1 and this as 2, and this is without subscript. So, let me write this as just Z and N for the first nucleus. So, this is Z and this is N, and this is Z1 and this is N1, and this is Z2 and this is N2. So, A is A1 plus 2, Z is Z1 plus Z2, and N is N1 plus N2. So, why this nucleus? So, it will be Z2 times MP and plus Z1 times MP plus N1 times Mn C square and minus. Now, this Y and Z roughly equal masses. So, it is half of it will come here, and here the binding energy per nucleon is 8.5 MeV. So, it is minus 8.5 MeV times A1. It has A1 nucleons. So, 8.5 MeV times A1, and similarly Mz you can write. So, Mz is equal to Z2 MP plus N2 C square and minus, since we assume that they are of the same order, the masses are of the same order. So, both of them are somewhere here. So, this also is 8.5 times A2. Now, you can work out this Q value, and the Q value will be, so this Q value will be mx c square and minus my c square, this is all c square here, and minus mz c square. So, when you subtract this part, this proton mass part and neutron mass part, that will cancel out, because z is equal to z1 plus z2. So, when you subtract this my c square and mz c square from mx c square, this part will all cancel out, and then you will have this one minus this one. So, these two will become positive and this will remain negative. So, it is 8.5 MeV, it is 8.5 MeV common A1 plus A2. So, this I have written these last two terms, this minus has become positive because I am subtracting these two quantities from this first one. So, these are positives, 8.5 MeV into A1 plus A2 and minus 7.6 MeV into A. So, minus 7.6 MeV into A, and A is equal to A1 plus A2. So, it is just 0.9 times A, and if you take A to be around 240, it is 0.9 into 240, and how much is that? That is 216 MeV. Positive, right? Positive. So, the rest mass decreases, and therefore, energetically it is favorable. System normally tries to go into that minimum rest mass energy, and if this nucleus splits into parts, roughly equal parts, the rest mass is decreasing, and therefore, this reaction is energetically favorable. And not only favorable, it yields about 216 mega electron volts of energy. So, if this reaction does take place, if this x goes into y plus z, where is this 216 MeV gone? The rest mass energy here is more, and it has decreased in this reaction. So, the rest mass of energy is less here. The remaining 216 MeV, where will it go? Primarily, it will go into the kinetic energies of these so called fission fragments. This reaction is fission reaction, and these two product nuclei are called fission fragments. So, when these two are created, they move in opposite directions with certain kinetic energy, and most of the 216 MeV is in that kinetic energy. There are some more things come out, gamma rays, neutrons, this and that, they carry kinetic energy. We will talk about this later. So, this much of energy is released. So, what is this minimum value of A, where this fission is energetically favorable? For 240, we have seen that yes, it is favorable. So, we can work out using semi empirical mass formula. Roughly I can see it here, this is around say 56 or so. So, if the starting point is double of this, then it will still land up this side, and landing this side means the binding energy per nucleon increases, and that is how from 7.6 it increased to 8.5, and therefore, you got that difference 0.9 times A as the decrease in rest mass energy. So, as long as the split nuclei are on the right side of this maximum, you will gain energy and this reaction will be energetically favorable. But if I start with a nucleus here and the split parts go this side, then one has to see which rest mass is less and which rest mass is more. A simple calculation can be made using semi empirical mass formula. So, the question is, what is the minimum A for this reaction fission to be energetically possible? Remember, I am talking of rest mass energies in ground states, no external energy given. If external energy is to be given, then anything can be broken. But just because of the difference in the rest masses, which system, whether the initial big nucleus or the pair of fission fragments, which is having lower rest mass energy, that we are looking at. So, no external energy involved. So, if I use this semi empirical mass formula, we have to look at various contributions to this mass, because we will be looking at this q value, whether this q is positive or q is negative. So, all these masses are involved and therefore, the binding energies are involved. Now, if you compare these two, let us take the case of say symmetric fission, A 1 is equal to A 2 and that is A by 2. Let us consider this situation where the nucleus is split in two equal parts, although in the normal fission reactions the probability of the symmetric fission is less than the asymmetric fission, where little bit difference is there in the two masses, but let us calculate for this. Now, in semi empirical mass formula, you remember the mass is of course, mass of a nucleus is that z times m n, that is written there, n times z times m p n times m n c square minus binding energy, and this binding energy is A v times A, this is the volume term, right, we had done it in the beginning, and then minus surface term A s A 2 by 3, and then a Coulomb term minus A c z z minus 1 over A power 1 by 3, and then there was an asymmetry term A sim n minus z square divided by A, and pairing term. Now, pairing term we will forget, this is when you have even A nucleus or odd A nucleus, odd nucleus, or even nucleus, or even odd even nucleus, that has its own differences in binding energy, but that we will forget here. We will assume that everything is even the original nucleus as well as the fission fragments. So, this we just neglect this. In other terms, this volume term, this is A v times number of nucleons. So, if the number of nucleons is same initial side and on the final side, it is a splitting, but the total number of nucleons remains same. So, A v times capital A, that will remain the same. Before the event, it is A v times capital A, and after the event you have two nuclei, A by 2 and A by 2. So, A v times A by 2 plus A v times A by 2. So, that will again become A v times A. So, that volume term in binding energy, it is same in the two situations, right. So, you have this A x going to A by 2 y and again A by 2 y, and if there is some difference in proton neutron you can call it Z. So, x going into y plus z, z is the name of the nucleus, not the proton number, right. So, this total A remains the same on the two sides, therefore, this volume term remains the same. What happens to the surface term? If you have one nucleus, assume it to be spherical. So, you have one nucleus and you have surface, and if this sphere is broken in two smaller spheres, the surface area will increase and therefore, the surface energy will increase. So, this term, the surface energy, this is going to increase, and the Coulomb term here, this Coulomb term, if you are separating it out, you are making it 2. So, essentially you are increasing the separation between protons on the average. So, if everything, all protons are in one sphere and then you split that and make it 2 spheres, 2 different spheres, at the end of it the Coulomb potential energy is going to decrease. So, the surface term in the binding energy and the Coulomb term in the binding energy, they are competing with each other. In splitting, the surface energy is increasing. So, the rest mass energy will increase corresponding to that. Coulomb energy is decreasing. So, the rest mass energy will decrease because of that. So, there is a competition between the two. What happens to this symmetry? This energy n and z are unequal. Because of that, you can work it out and you can see that this also remains unchanged. So, initially it was n minus z by a square, this was the initial term. So, let me call it just some a, and the after this split you have 2 of them. So, 2 times and n becomes n by 2 and z becomes z by 2 square of this weight. How do I write? This a should be outside. So, this bracket is smaller like this. So, this is square here and then divided by a by 2. So, for each fragment the asymmetry energy will be minus a sim and multiplied by n by 2 minus z by 2 square by a by 2. Whereas, in the beginning it was n minus z square by a multiplied by that asymmetry and that coefficient and minus sign and all those things, and these two happen to be equal, because this 2 and this 2 will become 4 and that will cancel this 4 and these two will be equal. So, that symmetry energy or asymmetry energy, whatever you call, n and z are not equal, therefore, there is a energy difference. So, that also remains the same in the initial nucleus and the 2 fragments. So, it is only the competition between the surface energy and the Coulomb energy. So, you can work out what happens to the total mass. Let me write mass times c square, some m naught c square and some constant. So, all these terms which are constant, the symmetry energy, the volume energy, these are constants are here, and that z protons are there, n neutrons are there, that is there, and minus binding energy, and from the binding energy those constant terms I have already written. So, here it is minus a s and then a to the power 2 by 3 and minus a c and then z, let me write it z square divided by a to the power 1 by 3. For these fission reactions, z is more than 50 or so. So, z minus 1 can be written as z. 2 fragments m 1 and m 2, they are equal. So, double of that, that is the final rest mass energy, and that will be this part will remain as such, because same number of neutrons, same number of protons, the volume term and the asymmetry terms, they are equal, and these two will become, so this whole thing multiplied by 2, and then this will be minus A s, and this will be A by 2 to the power 2 by 3, and minus A c z by 2 square, and divided by A by 2 to the power 1 by 3. So, that is this final rest mass energy, and if you subtract final rest mass energy from the initial rest mass energy, you get that Q value, and that should be positive if it is to be energetically favorable. Okay. So, you can work out the Q value m c square and minus 2 times m 1 c square. You can just write this minus this. So, you will have A s a to the power 2 by 3 and minus A by 2 to the power 2 by 3. So, and double of that, remember. So, that is the first term, and the second term is similarly plus A c z square divided by A to the power 1 by 3 minus 2 times and then z by 2 square and divided by A by 2 to the power 1 by 3. So, this quantity should be positive for fission to be, for this particular reaction, energetically favorable. Now, you can put the values of A s and A c, and that gives a condition just on z square by A, and then one can see for any given nucleus, if you want to check whether it should fission or not energetically. So, you can just put z and A in this equation and work out whether this Q value is positive or negative. And it turns out from this that if A is somewhere greater than 100 around, it is energetically possible. So, anything with A value greater than 100 should fission and reduce its energy. But we very well know that we have so many nuclei with A greater than 100, at least up to uranium 238 is uranium 235 and 238, and beyond also there are so many nuclei above this A equal to 100 mark, which in general are very stable. Right? In general, they are very stable, they are there and they do not fission by themselves. So, that was a question, a hard question, that if energy can be reduced by breaking this nucleus in two parts without giving any external energy, then how come these nuclei still exist? Why do not they fission and reduce their rest mass energy? And that once again using semi empirical mass formula, Bohr and Wheeler was able to tell why it is so. So, one has to understand the mechanism of this fission, how this fission proceeds, and Bohr and Wheeler gave this theory, very good theory, which explains almost all features, but fails at certain places. And that mechanism that was suggested again based on liquid drop model. This nucleus is considered as a spherical or nearly spherical drop in the beginning, and then before breaking in two parts, it must go through that intermediate deformation processes. So, the idea was that start with this spherical nucleus or nearly spherical nucleus, and then because of something, some energy deposition or something, if it starts deforming and finally it breaks, it has to go through those intermediate processes. And so, this will become something like an ellipsoid of the same volume, because nucleus is incompressible, right. The nuclear volume density is fixed, remains the same. So, the same volume is now in this shape, and then if it remember, it has to split. So, the next phase would be something like this, all this volume should be same. So, the drawing should be made accordingly, and then further deformation will take it like this, and then the two parts will just separate out, and finally, they will go, they are all positively charged, they will go away from each other. So, Bohr and Wheeler took some deformation parameters, and roughly speaking deformation parameter could be, think of this whole thing as two lobes, two masses, and the centers of that separation between them, that you can take as deformation parameter. So, if you have one single sphere, that means the two parts are all occupying that same volume and the deformation parameter is 0. So, here the deformation parameter, if I write it as r, that r is 0, and here you can say that okay, now if you think of two parts. So, one part is centered here, one part is centered here. So, one part is like this and one part is like this, so slight shifting. So, this r parameter is small and is this is that r parameter. Here this lobe is somewhere here and this lobe is somewhere here. So, the r parameter has, the deformation is increased. So, this is r. Similarly, here this is r. So, it is increasing. Right. So, this is how he quantitatively defined how much deformation is there in the intermediate states, and then for each shape, for each deformation, what should be the energy. The calculations are not easy, but what should be the energy using semi empirical mass formula. For example, what we need is surface energy. So, how much is the surface area of that deformed nucleus at each stage as a function of r. Similarly, Coulomb energy, if these protons are now distributed in this deformed dumbbell shape, what is the Coulomb energy. So, this is how all these things were calculated, and then from that what is the total energy, Coulomb energy plus surface energy. So, what is the total energy? Again there is a competition between Coulomb energy and surface energy. The surface is increasing and surface energy is increasing and Coulomb energy is decreasing. So, there is a competition. So, what happens when both things are taken into account, for different values of capital A, you get different kinds of this energy versus R dependence. So, in this vicinity of interest, where initial A value is around 240 or so, the shape turns out to be something of this sort. So, on the horizontal axis we are showing this deformation parameter, and here we are showing that energy, and 0 of energy is taken when these two fragments are well separated. So, the Coulomb energy is also 0, they are well separated. So, once they are well separated and distance between these two fragments is large, there is no nuclear interaction. So, this portion here is essentially that Coulomb part Z1 Z2 E square over 4 pi epsilon naught r, and with respect to this 0, where the two fragments are very widely separated, calling that as 0. When it was one single nucleus, the rest mass energy was higher. If I consider that A equal to 240, it is something like 216 MeV higher. So, that is this value, that is this value here, 0 deformation. right. So, this is that Q value of that reaction, and intermediate between this value and this value, as the deformation starts, the energy increases, and then it goes through a maximum, and after that it decreases, and finally, it just goes as 1 by r dependence. So, this is the kind of dependence of this energy, which includes surface energy as well as Coulomb energy, and this maximum, this value, the highest value of energy minus this 0 deformation energy, this is known as activation energy or barrier height. You can also call it barrier height. It is a potential barrier. Okay. So, the fission has to go through this potential barrier to really get to that fragment state. So, this barrier is the answer to the question that why do we have stable or very stable nuclei beyond that A greater than 100. So, this extra energy, when you have a nucleus in its ground state, it has this much of energy. If the nucleus splits in two parts, it will have this much of energy. So, the rest mass energy will be decreased, but the intermediate processes, the intermediate states, the intermediate deformed shapes of the nuclei will undergo through these energies, and therefore, you have this barrier. The total available energy is this much, whereas this barrier is to be surmounted, this extra energy is needed. This is activation energy or barrier height. This is perhaps somewhere around here. This means perhaps you have some kind of deformation in this state. If it is further deformed, the energy decreases, but in the beginning it is this. So, for different A values, this barrier height is different, and for A equal to 240 or in that range, of course, it will be a sensitive function of A. So, somewhere around say 240 region, this activation energy or barrier height is something like say 5.5 MeV to 6 or 6.5 MeV, something of this sort, of this type. So, this much of extra energy is needed, and that is why the probability is very small, and that is why we have almost stable nuclei. Okay. But if you look for much larger values of A, then there is no barrier. In fact, this shape does not work. From the very beginning, as the nucleus start deforming, the energy start decreasing. If that be the case, then of course, you will not have those nuclei, they will spontaneously fission. We can work out that condition also, where a small deformation triggers larger deformation. It is like unstable equilibrium of an object. If you disturb it slightly, that triggers larger disturbance and it falls. So, similarly, if you consider very large nuclei and in spherical shape, it will have some energy and slightly deform, and the decrease in energy starts right from there. It does not increase and then decrease. In that cases, you will not have any barrier. So, if you want to work out the condition for that, you have to do little bit of geometry. If you have a sphere of radius say r and you deform it slightly in that ellipsoid shape, the first stage, let us say, of this type. So, if you deform it here and if it takes a prolate type of ellipsoid shape, then this radius is larger and these radii are smaller. The drawing does not suggest that, but does not matter. This is B and this is B. and the volume should be same. So, the volume here is 4 by 3 pi r cube, and the volume there is 4 by 3 pi a b square. So, the volume should be same, nuclear density is same, and if I write this A as r times 1 plus epsilon, this radius is increased here, it is elongated, and this is compressed. So, B will decrease. So, if I write this A as r times A plus 1 plus epsilon, I can put it here and see what is B. So, you have r cube is equal to A B square. So, you have r 1 minus 1 plus epsilon, that is A, and B square, and from here you can work out what is B. So, B will turn out to be r square, and square root of that is this, and this by 1 plus epsilon. So, if the volume is to be kept same, and if this A is increased by 1 plus epsilon factor, then B should decrease by 1 by square root of 1 plus epsilon. With this geometry, one can work out how much is the increase in surface area and how much is the decrease in Coulomb energy. So, the surface area, that becomes S into 1 plus 2 by 5 epsilon square up to order epsilon square. So, you have higher order terms that I am not writing. So, the surface area becomes this much, and therefore, if you look in terms of the surface energy. So, A s a to the power 2 by 3, it will be multiplied by 1 plus 2 by 5 epsilon square. The area is increased by this much. Now, Coulomb energy, once again one has to make a tedious calculation how much is Coulomb energy. It will decrease because things are getting separated. So, it will decrease, and this Coulomb energy becomes A c times z square by A 1 by 3, and then 1 minus 1 by 5 epsilon square. Okay. So, the net increase should become negative if you do not want any barrier. So, net increase will be equal to A s capital A 2 by 3 times 2 by 5 epsilon square, this is the increase, and then minus this A c z square by A 1 by 3 and times 1 by 5 epsilon square. Okay. So, the Coulomb energy is decreased, the surface energy is increased. We are writing the amount by which the surface energy is increased minus the amount by which that Coulomb energy is decreased. So, this is the net increase. Now, you can ask, when you do not have any increase, give a small deformation and the energy starts decreasing. That will be the case if this quantity happens to be less than 0. So, even a small deformation decreases energy. So, this is the condition, and you can now cancel that epsilon square and other things, and you can get a condition once again on z square by A, and this turns out to be using the same value of A s and A c. A c is 0.72 MeV and A s is 16.4 MeV. Z square by A turns out to be around 47. And if you take Z equal to 0.4 times A for a rough calculation, for uranium 238 this value is 0.38 or so, Z by A. So, if you take this value, this relation will say that A is roughly greater than 300. So, these calculations will suggest that if you have if you somehow create a nucleus with A greater than 300, it will immediately fission in 2 parts, because there is no potential barrier. So, this is all about the spontaneous fission or fission by itself, and energies, rest mass energies and so on. No external energy is given, but the fission that we are using most of the time for our power generation and in many other situations is induced fission, where you have some kind of a stable or very stable kind of nucleus, heavy nucleus, and it is not going to fission any as such because of that fission barrier, but then we put some energy into it, we pump some energy into it, and that energy makes it capable of surmounting that fission barrier. And when that happens, you call that as induced fission. Now, induced fission can be because of any kind of nuclear reaction that we trigger. We can also trigger it with just gamma photons. So, if we have a nucleus and if we put gamma photon on it, it can go to its excited state, and depending on how much energy we have given to it, it can surmount the barrier, and then this can fission. This is known as photofission. So, fission by photons, fission induced by photons, photofission. In fact, this reaction is a very good reaction to experimentally measure the activation energy, because there are no extra neutrons or nucleons we are putting in, is the same nucleus, we are not changing the nucleus, only energy is being deposited. So, if we give a small amount of energy, the barrier is not surmounted, the fission probability is very small, negligible. And as you keep on increasing this gamma photon, that fission cross section will increase exponentially, barrier penetration, because that height to be penetrated and the width to be penetrated is small. Remember, you have this kind of barrier, and this is that. So, if you put this much of energy, this width is to be penetrated, and if you put this much of energy, then this width is to be penetrated. So, width is decreasing as well as the height is decreasing, and the probability of this reaction goes up. And once you have given this much of energy, so that the barrier is over, barrier is surmounted, then the fission cross section will suddenly rise manifold. So, by looking at the energy of the gamma photons required to trigger this fission with large cross section, one can make calculations and work out from this experimental data the actual activation energy, the actual height of the barrier, and one can match with the model calculations and all those things. So, that is this. Similarly, you can have other particles going in A and then some other particles going in. The most important one which we will talk in detail is neutron. So, now the nucleus is different, this nucleus is now different, call it B, and that is in excited state. This is captured, this is absorbed, so that becomes B star, and this fissions. So, compound nucleus type reaction. So, when this happens, then depending on the Q value, if the Q value is positive, then that energy is made available, because if the rest mass energy goes down, this side rest mass energy is more, this side rest mass energy is less, then that extra energy must be there in the nucleus somewhere. And in this reaction, you do not have much of kinetic energy involved, right. If it has a kinetic energy n, then this will also have a kinetic energy to conserve the linear momentum, but then we had made calculations in previous lecture that this kinetic energy will be much smaller. It will be smaller by a fraction of say this mass of this neutron divided by mass of this particle. So, that kinetic energy part is almost negligible. So, the entire that Q value and any kinetic energy which is there in this neutron becomes the energy above the rest mass energy or above the ground state, and therefore, the total energy is raised by that much. And if that is enough to surmount the fission barrier, the fission will take place. If it is not, then that barrier penetration and low cross sections and all those things will happen. So, we will continue from here.